reactions, what fuels them, what they need, how they operate. I will remind you that this is a PowerPoint that I'm using from another teacher. There is one slide that has a picture on there where I just don't get how it goes, but we'll see if you guys can figure it out.
Make it. Nothing. Wow, you
All right, so metabolism is all of the chemical reactions that are occurring in a cell at any given time. It's the flow of energy in and out all together. So we're not looking at one specific set of reactions here. We're looking at all reactions occurring in a living organism at the exact same time. Remember, all living organisms have multiple reactions happening. We're not focused on one thing at one time.
Does that mean when people say they have a fast metabolism, their cells work faster?
People who typically have a fast metabolism are really efficient at breaking down energy sources that come in.
Well, that's what does exercise affect your metabolism?
It can, yes.
Like,
because if you've got an increased energy demand, you're going to need that energy quicker. And you're going to need more of it. So instead of storing it and holding on to it for later, you're going to be using it.
so then, like, say I do sport and then I'm eating, like, I lose everything, right? So it doesn't go towards, like, fat.
It depends on how much you're taking in versus how much you're burning off. If you're taking in the same amount you're burning off, there's going to be no net gain or increase or decrease. Just because you're an elite level athlete, if you're eating 20,000, really?
For real?
If you're eating 20,000 calories, you're probably still going to gain weight. That being said, a typical athlete like Michael Phelps was talking about, his daily average intake for calories was 12 to 15,000.
I'm tired of doing floats. I've been doing it for 3 years now. I'm tired.
Taking about 2,000 on average daily basis. But when you're training for
Some of
hours,
total chemical reactions that occur within the cell.
it's about working out helps. You still don't want to go eat a whole pizza by yourself.
Pizza is bomb, though.
All right. So metabolism, sum total of all energy being used and released at the same time, means that we're combining anabolism plus catabolism. We're going to define those in the next couple slides here. Anabolism is the process of building material. So we're taking smaller pieces, making larger molecules with them. The example listed on the board is protein synthesis. We've got individual monomers with the amino acids, and we actually have to go through a chemical reaction or process to link these things together to create our proteins. That's an example of going from small to large. That would be an anabolic reaction.
So they have to remove water to combine?
Yes. We good? Alright, then the opposite is catabolism. So we're taking these larger molecules, breaking them down into their smaller pieces. An example of this would be cellular respiration, where we're taking ATP or energy and breaking it apart so that we can actually harvest that energy. When we're talking about energy, we have to fall into two specific laws. transformed, but it cannot be created and it cannot be destroyed. So all we can do is take energy and convert it from one type of energy to another type of energy, but we can't outright create it and we can't destroy it and completely get rid of it. All energy in the universe is here. It's a fixed amount. We can just transform it, but we cannot create or destroy it.
What if we can't create anything? Does that mean we never get tired?
Yes, theoretically, I don't know, because we can't create it, so
I was doing animation.
My friend was telling me that there's this guy that can run forever because something in his like muscles like allow him to keep on running, he never get tired.
So if we make ACT constantly?
I'd love to see that article.
I don't know.
Hey, imagine a swimmer.
At some point, your body needs to recover.
Yeah.
Not this guy.
Until you said him, I was like, how was that? I get tired of it, so he has to get tired.
I'd love to see it.
Every energy transfer is short issues.
So every time we transform energy or move energy from one source to another, according to the second law of thermodynamics, it increases the randomness of the universe. You're kind of moving things all over the place. It's not a set, static spot.
Is energy made out of atoms also? What's energy?
Let me get back to you. I don't know what a good term for energy is other than
I don't see it
ATP.
big.
So, other than what fuels chemical reactions. Alright, most energy is lost to the environment in the form of heat. So we're not very efficient at using our energy. Almost 75% of energy is lost to the environment. Okay, this next slide, this slide, I don't get the picture. So you guys tell me if it makes sense to you. Good?
Well, heat is the lowest quality. Is that? Oh, it's a guy.
But what does that have to do with heat being the
He's
lowest
creating
quality
heat.
of energy?
He's creating heat, but then it goes away quickly.
Isn't it the opposite? Isn't it contradicting? Because
I
that's showing power.
I don't
What
know
game
the
is that
game.
from?
I don't get the picture.
That's mom.
Heat is the lowest quality of energy, so it's not a very efficient source.
What's the highest quality of energy?
Something with ATP. I was expecting someone to do the chart.
I was expecting someone naked.
Why naked though?
No. I wonder who that is.
It's the guy from
No, we don't know.
the
Ah.
Street Fighter.
Oh wait.
Oh, it might be Street Fighter. That would make sense.
It's supposed to say loss, not lost. So energy released in a system that is used to do work without loss to the organism or the cell. Meaning that that organism has the ability to release energy to fuel its processes, but the overall cost to the cell is neutral. It's not actually costing the cell any of its energy reserves. So common sense would tell us the more free energy we have, the more ready and able we are to actually do work or perform a function. So it's not costing us anything. The less free energy we have, the less work we're capable of doing. Because at some point, if we're out of free energy, we're going to have to start going to that energy reserve, and it's going to start costing us energy.
Do you want these tables on there too?
Oh, okay. I get bored.
Good?
Here.
All right. Since you guys said I could erase this, I'm going to redraw this because I'd like you to draw the graph in your notes, but it's kind of hard to see.
No, this animation makes no sense. Oh, I wish I could zoom in. So exergonic reactions are releasing energy. We've got a whole lot of reactants here. We've got a whole lot of stuff ready and able to do work. The reaction goes, we end up with a whole lot of product. So we release energy. Everything's the same except your this time energy is required. We're using free energy. So instead of releasing free energy, we're using the available free energy. Instead of Energonic uses free energy, so we're taking the available energy to actually form a product instead of breaking down a product and releasing energy.
Then ender exergonic.
Releases energy. So that's opposite of this. We good?
Miss Whitaker,
Yeah.
is it still the amount of energy released?
Yes. So from here to here, we're not, that, it's a positive.